Today we will discuss the GG1 queue and a very important result in queuing known as Little's theorem, which relates the average occupancy of a queuing system to the average waiting time in the queuing system. Okay. So, we will discuss the GG1 queue a little bit and we will prove Little's theorem using the renewal reward approach that we have developed for the GG1 queue. Okay. Although the Little's theorem itself is not just limited to GG1 queues, it is actually applicable even to multi-server systems, okay, as we will see, but we will prove it only for GG1. Okay. That is today's agenda. So, you guys already know what a GG1 queue is. So, this is a server and this is a queue. You have renewal arrivals, okay, according to some distribution x. Okay. So, xi's are inter arrivals and the service times of each jobs are also IID. Okay. Now, so this is actually what is usually known as a GI-GI1 queue. Okay. You have independence between consecutive service times and independence between consecutive arrival times. Okay. So, some people write GI-GI1, but usually GG1 means without any further qualifications usually means GI-GI1. Okay. So, you can look at IID. So, so arrival times, arrival process is a renewal process with inter arrival times xi's, okay, and expected x, let us say 1 by lambda, lambda is the arrival rate and this is assumed to be finite. Okay. And the service process, so each customer, whenever this renewal process ticks, there is a customer that arrives, right. So, if you look at the time axis, let us say this is time 0. Okay. So, you have some renewal arrivals, okay, and whenever this arrival occurs, there is a customer who comes to the system and each customer brings with him or her an inherent service time. Okay. So, we assume that the server works at a constant rate, let us say 1, okay, and you can think of these customers as bringing with them a certain file size or job size or whatever, right. So, some could be large and some could be small, all right, and what we are saying is that these random variables are also IID, this file size or customer service time random variables are also IID. Okay. So, these are the file sizes are let us say Vi. Okay. So, Vi, so you can say that the server serves at a constant rate 1 and each file of size Vi will take an amount of time Vi to get served at the server. Okay. So, we assume that the service time of customer I is also is some Vi. Okay. Which are also IID. Okay. Okay. And we will say xi's and so this sequence xi is independent of this sequence Vi. Okay. Well, this sequence Vi, I will write I greater than or equal to 0 because for the GG1 queue the convenient convention is to start ticking time when the first arrival comes to the system. Okay. The system is empty for a very long time, it is there is nobody at all and then suddenly the first arrival comes and you start accounting time at that point. Okay. So, what we will do is you can take the first arrival at 0. Okay. So, in some sense it is a renewal process after time 0, there is a first arrival at time 0 always because you are starting your clock at that time. Okay. So, this you can think of as a customer with file size V0 who comes to the system at 0 time 0, starts getting served, and then the subsequent arrivals are renewal intervals, I mean renewal arrivals, and each of course brings in a job size or file size or customer service time Vi. Okay. So, this Xi's are IID, Vi's are IID. Again we can write expectation of V as 1 over mu. Okay. So, also assumed to be finite, and Xi's are independent of Vi's. Okay. So, this is the model of a GG1 queue. So, the arrival distribution can be anything, inter arrival distribution can be anything, service time distribution can be anything, they just cannot be correlated among themselves or across the Xi's and V's. Okay. That is the GG1 queue for you. Okay. Now, we are interested in characterizing we are interested in looking at the waiting times of these files or these customers in queue. Okay. The usual notation is Wi is taken as the total, I mean is notation for total notation, total time spent in the system by customer I. Okay. And the book uses Wi q, Wi. So, these are random variables, right. So, these are big capital letters, okay, just in case you are confused. Wi q is the time spent waiting in the queue. By customer I. Okay. So, what is the difference between Wi and Wiq? Wi is the total from the time the customer I arrives at the system, wait, get into service, finish service and get out, that is the total system time. Wiq is simply the time spent waiting, not including the time getting served. Okay. So, Wi is basically the Wiq plus your own service time you spent getting served yourself. Okay. Now, we are going to do, I have to specify the service discipline, I am going to do only first come first served, okay, in class, but I will also point out why this FCFS is not, I mean much of what we are going to say in today's lecture will hold for other service disciplines as well, but FCFS is probably the most intuitive and most common. Okay. So, this is first come first serve. So, customers are served in the order in which they arrive. Okay. So, a person who came earlier will be served earlier. Okay. This is I mean this is not of course necessary, right, you can do something else also. I am just going to analyze this situation, FCFS situation. So, please remember that there is the time begins when the 0th customer comes at time 0 with some file size V0, okay, that is when we are starting time. Okay. So, I want to just plot for you the evolution of this FCFS queue, okay, GG1 queue. So, the first arrival happens at time 0, right. So, let me plot the arrival process. The arrival process has 1 plus NT, where NT is the renewal process, right. So, it starts at time 0, okay, and there is another arrival, there is an arrival here, let us say. So, this is just the arrival process, okay, I am plotting the arrival process. Okay. Let us say this one more arrival and so on. Okay. So, this I can call it as arrival process, this is t time of course, I am going to call it A of t is equal to n of t plus 1, this n of t is the arrival process, okay, renewal process n of t. Okay. Why am I adding plus 1? There is a arrival at 0 always, after that you are counting renewals. Okay. Now, I also want to plot the departure process. Okay. So, this is the arrival process, then this is FCFS and I want to plot the departure process. So, the customer who arrives at 0 starts getting served at 0, right, he comes to an empty system, correct. Now, how long will he be in the system, the first customer to come at 0? His service time, which is V 0, right. So, his departure will occur at time V 0, right. So, let us say, so this let us say that is my departure process, I am drawing this in blue. Okay. So, this length, if you look at it, right, this length will be equal to, this length will be V 0, correct. Of course, these lengths are your exercise, maybe I should not, here I should not write apologies. So, this is your, these are realizations, right. So, maybe you should write, so this is like x 1, right, x 1 is equal to little x 1, this is x 2, that is x 3 and so on, these are the inter arrival times, right. And this V 0 is some little V 0, right, and when this guy leaves, the second person gets into service. So, the second customer who gets into service at this point is the person who arrived over here, is that right. So, that person gets served for some time and he leaves, okay, and then the person who came here gets into service, the second arrival not counting the arrival at 0, right, gets into service, all right, and in this picture let us say he finishes service. Okay. So, in my picture, so this guy is V 1, guy is V 2, this interval, right, this interval is V 2. So, V 1 corresponds to the service time of the customer who entered here, correct, and V 2 corresponds to the service time of the customer who entered here. So, at this point what have, how many people are there in the system, at this point how many people are in the system, system has emptied, right, and then and in this small duration system is empty, right, and then there is another arrival and so on, correct. The similar sort of a thing repeats. Okay. Now, a key fact that we will argue prove at least prove using pictures, okay, we can make this very rigorous easily, is that consecutive arrivals to an empty system constitute consecutive arrival epochs to an empty system constitute renewals. Okay. This is a key fact. So, what do I mean? So, if you look at this picture, at time 0 you had an arrival to a empty system. Okay. And what is the next arrival that occurs to an empty system? This guy, right, this guy, right. This is like the first arrival to an empty system, of course not counting the 0th arrival to the empty system, right. The time at 0 is the beginning of time, a bunch of arrivals come and they leave, and then there is another arrival to an empty system. Now of course the similar sort of a thing plays out, right. This guy getting served, more people will come and so on, and let us say the system empties again, and one more time there will be an arrival to the empty system, right. What we are saying is that these durations constitute renewals. Okay. So that is what we are going to show. Okay. This is not all that difficult to see, because in some sense, see, if you have if your system emptied out, right, statistically what is going to happen after if you have an arrival to an empty system, statistically what is going to play out again is the same as what played out starting at t equal to 0, right. You again have some arrivals which have inter arrival times are renewals and service times are IID, right. I am not saying they will be equal, of course they will be different, but statistically they will be the same, and statistically they will also be independent, because all these xi's and vi's are independent. You see what I mean? So that is what we have to argue. Now to understand why this is true, I want to be able to track how long these customers wait, okay, before they get into service. Okay. Of course the arrival at 0 waits for 0 time, right. The second arrival which occurs after the first, after t equal to 0, how long does that person wait? The x1 arrival, so to speak, waits till the 0 arrival completes service, right. So the amount of, so this is the amount of time that for customer number 1 waits, correct, in queue before getting into service. So this should be W1 Q, all right. So in this picture I can write W1 Q is equal to I can write this in terms of random variables, all right. So I have drawn specific realizations. I can write W1 Q is equal to how much, V0 minus x1, correct. But see, in my picture V0 is bigger than x1, but if the amount of time, if x1 the first arrival took place after V0 completed, then what happens, the waiting time will again be 0, right. So if V0 minus x1 is negative, then I should count this as 0, I should not count negative time. So I can put plus max of whatever this is comma 0, okay. So basically I am using the notation y plus is equal to max of 0 comma y, okay. Now what happens to the second customer, the x2 arrival, so to speak, waits for that much time, right, correct. So what is W2Q, can you tell me a similar equation? I would like it in terms of the previous waiting time. So it will be W1Q plus V1 minus x2, right. So what am I saying? So it is W2Q is simply it is the time that it arrived. So this this total length, right, is W1Q plus V1 minus x2, right, will be W2Q, right. So let me just write it out. Way I have written it is W1Q plus V1 minus x2, okay, the plus will come for the same reason. If this is negative, you will have to count it as 0, right. So, you can generally say, you can keep doing this, right. You can write for the ith customer, you can write WIQ is equal to WI minus 1 Q plus VI minus 1 minus XI whole plus, okay. If this turned out to be negative, then you will put 0, right. This is true for I greater than or equal to 2, all right. So, if you take, so this bunch of equations, right, actually I can actually just delete the second equation, it is just a consequence of it is contained in the third. So, this is this bunch of recursive equations are known as Lindley's recursion, okay. It is a recursive equation you can write to characterize the waiting time of the ith customer in terms of the waiting time of the I minus 1 customer and the Xi's and Vi's. See, these Xi's and Vi's are given to you, right, I mean those distributions are known to you, right, and you are able to write these waiting times in terms of these Xi's and Vi's and the previous waiting times, okay. Is that clear? This is for a first come first serve GG1Q, okay. Now, we want to see the 0, that arrival at time 0 had 0 waiting time, it did not wait at all, right. Now, what is the index of the next arrival for which faces 0 waiting time, right. So, in our picture for example, the x1 arrival, the first arrival not counting the arrival at 0 has some positive waiting time, right, W1Q, and then W2Q was also positive, and the third arrival which happened to an empty system had 0 waiting time, right. If you think about why this happened, right, what is it about that the third arrival in terms of the Xi's and Vi's that helped it face 0 waiting time? See, it is the first arrival for which the sum of the Xi's is greater than or equal to the sum of the previous Vi's. See, for the first arrival V0 was bigger than x1, right. For the second arrival also W2Q was positive because V0 plus V1 was bigger than x1 plus x2, correct. But for the third arrival, that x3 is quite large in the way I have drawn it, right. It turns out that the x1 plus x2 plus x3, which is the epoch S3 of the third arrival epoch, is larger than the sum of the service times of all the customers who come before, correct. In fact, you can see this from the Lindley's recursions, okay. WIQ equal to 0 for the first time, what is the smallest I for which WIQ equal to 0 will also be the first index for which the sum of Xi's till that particular index is exceeds the sum of the Vi minus 1, I guess, right. Okay, so, I am going to write it like this. So, index of the first arrival, so after t equal to 0, okay, which enters empty system is the smallest n that satisfies WNQ equal to 0, right. This is the thing about the first arrival which is an empty system, right. This is equivalent to the smallest n for which sum over I equals 1 to n x I is greater than or equal to sum over I equal to 1 to n v I minus 1. Okay. In the picture I have drawn, this n is 3. Okay. Now I will argue, so this, so what does this depend on, right? So you think about this, you are looking at, so you have a bunch of random variables, forget about the queuing system, right? You have a bunch of IID random variables xi's, you are given a bunch of IID random variables vi's, vi minus 1, right? And I am asking you, you keep looking at these xi's and vi's and tell me the first time that sum over xi's exceeds sum over vi minus 1. Now what does this sound like? This sounds like something we have already studied. Okay, so let me put it this way, right. So I can write this as the smallest n, equivalently the smallest n for which sum over I equals 1 to n xi minus vi minus 1 is greater than or equal to 0. See, you call xi minus vi minus 1 as some other variable yi, they are also IID, right. So you are looking at the first time that these yi's could be positive or negative, and we are looking at the first n such that sum over yi is non negative. What does this sound like? See, this is like a stopping rule, except that there are two sequences of random variables. Okay. So you know what a sequence of, I mean a stopping rule j for a sequence of random variables xi, right. You look at each n, you look at just the first n realizations and decide to stop or not, right. Now I am going to look at not just xi's, I have a bunch of xi's, I have a bunch of vi's, and I am going to look at both and I am going to stop whenever sum over xi's exceeds greater than or equal to sum over vi minus 1. So I can write a stopping rule j as the minimum of n such that okay. Now clearly the event you can argue, right. So you are only looking at x1 through, whether you stop at n depends only on x1 through xn and v0 through vn minus 1. Okay. So is j is a stopping rule, it could be defective, right. It is not clear that you will eventually see a arrival to an empty system. What if the queue keeps building up or something, right. It could be defective, possibly defective, for not just xi's but xi vi minus 1 okay. So you can define, this is like a slightly generalized version of stopping rule, where you do not have just one sequence, you have two sequences, it does not matter, right. You are only looking at, so whether you stop at time n or not is dependent only on the information available at that time, you are not looking ahead, you are looking at x1 through xn and v0 through vn minus 1. Okay. Remember j is not a time, j is an index, okay. That is why I am writing stopping rule instead of saying stopping time, right. It is the index of the arrival, it is not actual time. Okay. Now what we will see is that j is a genuine stopping rule, not a defective stopping rule, if the average inter arrival duration is greater than the average service duration. If expected x is greater than expected v, then j is a legitimate stopping rule, which means that you will stop infinite, you know, you will always have an arrival with probability 1 which enters in this empty system. Furthermore, if expected x is greater than expected v, you can show that expected j is finite, okay, slightly non trivial, but you can show it, okay. And what we can also show is that once the stopping rule realizes as j is equal to some n, okay, then the subsequent arrivals, let us say conditioned on j equal to n, the subsequent inter-arrival times will be xn plus 1 etcetera, right. In our case n is equal to 3, right, then the subsequent inter-arrival times are xn plus 1 etcetera, and this subsequent service times are vn minus 1 vn etcetera, correct. And again Lindley's equation can be written for the subsequent waiting times and all that, right. Now, you can also argue that condition on j equal to n, okay, if your condition on j equal to n, what are the inter-arrival times xn plus 1 etcetera, which are independent of the previous, the inter-arrival times in the previous busy period, so to speak, when the server was busy, right, and likewise for the vn's, right, vn minus 1 vn plus 1 etcetera are independent of the previous service times. And all these for every n you are conditioning on j equal to n, these random variables xn plus 1 etcetera and vn etcetera are independent of j and independent of the previous xi's and v's, right, in the previous busy period. So, you can basically argue, I have argued independence and identical distribution, right, conditioned on j equal to n, but this is true for every n, right. So, you basically argued that these are renewals, right. What do I mean by these are renewals? The times at which there are consecutive customer entries to a empty system, these constitute renewals, okay. So, we will state this as a theorem. For GG1 Q with expected x greater than expected v, i.e. lambda less than mu, right. Thus, subsequence of that C an empty system a renewal process. The expected number of arrivals between arrivals to an empty system is finite and the expected time between successive busy periods between the commencement of successive busy periods is equal to expected j times expected x. This is the expected interrenewal duration. So, I have used a term here busy periods, right. So, you go back to this picture. So, this particular picture shows one busy period. So, you have somebody an arrival to a empty system, then there is a whole queue build up, wait, everybody leaves, and then the system empties, and then there is another arrival, right. So, we are saying these intervals, successive intervals constitute renewal duration, and this is one busy period basically. Okay. So, what we are saying is that so we are saying two things. Let us go back to the theorem now. We are saying that the subsequence of arrivals that see an empty system form a renewal process. So, what do you mean by subsequence? You have a arrival sequence, right, x1, x2, this is a renewal process to begin with, but not all of them see a empty system. There is a subsequence that sees an empty system. So, in our picture the first arrival of course sees an empty system, I mean first arrival, at 0th arrival sees an empty system, then the third arrival sees an empty system, then maybe the 7th and the 13th or whatever see an empty system, right. We are saying that particular sequence, right, that particular subsequence of this exercise itself constitutes a renewal process. Okay. And we are also saying that j, which is the stopping rule, which is the minimum x, which is the first index for which you see a empty system, this j is a legitimate stopping rule with finite expectation, okay, that we have not proved. Okay. It is not difficult to prove it, I think there is an exercise in your book. It uses a truncation argument. You have to use interarrival distributions which are bounded, prove it for that, and then you use a truncation argument, okay, for proving expectation if j is finite. And then the expected real time, the continuous time between one arrival which is an empty system and the next arrival which is an empty system, the expected time will simply be, it is like expected Sj, right, which is just by Wald, right, expected j times expected x, okay, which will also be finite if expectation of x is greater than expectation of v, that is the arrival rate should be less than the service rate. Lambda is the arrival rate which is 1 over expected x and mu is 1 over expected v. So, lambda is less than v, then we are guaranteed that you will have infinitely many of these entries to empty systems, okay, empty systems, and the expected duration between these renewals, this expected renewal time will also be finite, which is just expected j times expected x. Okay. Now, we will use this bigger renewal process, this what I call the subsequence, which these empty systems, to prove Little's theorem. Okay. That will be our discussion next class.